Hello friend, welcome to this lecture. In this lecture we continue our study of regular Sturm-Liouville boundary value problem, and in previous lecture we have discussed the existence of eigenvalue and eigenfunctions, and we have discussed some of the properties of eigenfunction, which is one very important property of eigenfunction, that is orthogonality with respect to weight function. So there we have assumed two type of boundary conditions. So let me write it here. We have considered this Sturm-Liouville equation, that is Px dash dash plus Qx plus lambda Rx equal to 0 here. So this equation is known as Sturm-Liouville equation, and here this x dash means dx by dt. So t is ranging between a to b here, and we have discussed two type of boundary condition, that is one is separated boundary condition, that is m1 xa plus m2 x dash a equal to 0, and this is defined at the point x equal to a t equal to a, and then other boundary condition, that is m3 x b plus m4 x dash b equal to 0. So this is defined at a and this is defined at b. So this is one type of boundary condition and another type of boundary condition is periodic boundary conditions, that is pa equal to pb. P is a coefficient of x double dash, so pa equal to pb, xa equal to xb, and x dash a equal to x dash b. So this is periodic boundary condition, and with the help of this we have also shown that pw, say x1 x2 given at a and b is coming out to be 0. That is the content of the last two results. So here w x1 x2 is Wronskian of x1 and x2, where x1 and x2 are two linearly independent solution of SL equation. So here it is x1 x2 dash minus x1 dash x2. So here we have shown that it satisfies this particular property. Now we are discussing one more important property of eigenfunctions with Sturm-Liouville problem. So that property is that let the hypothesis of theorem 15 holds. This theorem 15 is the existence of eigenvalues and eigenfunction, and also suppose that RT is positive on the entire interval AB, or RT is negative or on A comma b. So it means that RT is non-zero in this particular interval, whether it is positive or negative, it will keep one sign only. Then in this case, then all the eigenvalues of boundary value problem 12 along with 13a 13b boundary condition, or 12 with 14 are real. Here 12 is this SL equation, and 13a 13b are separated boundary condition, and 14 is the periodic boundary condition. So it says that if R is positive or R is negative, then and it satisfies all the condition of the theorem 15, that is that A and B are finite and coefficient P is positive, it means that it is also non-zero, then the eigenvalues of this are all real. So eigenvalues of 12 or 13a or 13a 13b or 12 with 14 are all real. That is what we wanted to show in this particular theorem. So let us assume that that lambda is a complex. We want to prove that it is real. So let us first assume that it is a complex, and then we try to show that it is not the case. So let lambda equal to a plus ib. So where a and b are both are real constants, be an eigenvalue, and corresponding eigenfunctions are given at xt, which is again complex. We are assuming mt plus int be a corresponding eigenfunction of the given boundary value problem. So whether it is 12a 13a, so it is either 12a 13a 13b or 12 or 14. So here boundary value problem is either this one, so any of these. So it is already clear that by assumption a and b are constant and mt and nt are real valued function. So using the values of lambda and corresponding eigenfunction, we now put it the values of lambda and the corresponding eigenfunction here in px dash dash plus qx plus lambda rx equal to 0. So here we are putting the value of x and lambda. So it is p, so this is x dash is m dash plus I n. So here x dash is basically m dash plus I n dash. So we are writing here plus qx plus lambda r and x equal to 0. So once we have put it here, then we simplify this in terms of real and imaginary part. So when you equate the real and imaginary part, here I can write 0 plus this 0 is basically 0 plus I 0. So equating the real and imaginary part, we have the following two equation, that is Pm dash dash plus q plus arm minus brn equal to 0, and Pn dash whole dash plus q plus arn plus brm equal to 0. That is not very difficult to look at here. So if you look at, this is what here it is, Pm dash, and then okay. So here you have to do little bit calculation. So once if you do the calculation, then you can get that it satisfy these two equations here. Okay. So now once we have these two equation, then we want to ultimately our aim is to prove that this b is basically 0. If b is 0, then lambda is real. So we want to prove that this b is 0. So what we try to do here, let us simplify this, and for simplifying this, you just multiply the first equation by n and second equation by m and try to make it simple. So when you eliminate q plus ar in the above two equalities, means you just multiply n here, you multiply m here, then you can eliminate and you subtract these two, then you can eliminate this q plus ar. So when you do this thing, then what you will have, let me write it here, it is Pm dash whole dash n plus q plus ar mn minus br n square equal to 0. Similarly, second equation is Pn dash whole dash m plus q plus ar multiplied by mn plus br m square equal to 0. When you subtract these two, minus minus minus, so this will cancel out. So what you will get is the following thing, that minus b into m square plus n square r, that is the last term. If you look at here, if you look at this thing, then we have b r n square plus m square, that is what it is written here, minus b m square plus n square r, and the opposite side we have this thing, that m p n dash whole dash minus n p m dash whole dash. So that is what I have written here. So now we have already seen that this can be simplified further, and this can be written as d by dt of Pn dash m minus Pm dash n. So this we have, because if you simplify this, you will see that you will get this. So here we have this equation, minus b r m square plus n square equal to d by dt Pn dash m minus Pm dash n. Now what we do, we just integrate with respect to t from a to b. So what you will get, minus b is just a constant, so we can take it out. So minus b integration from a to b, m square s plus n square s and rs ds, and here since it is a derivative with respect to t, and if we integrate, you will get Pn dash m minus Pm dash n from b to a. Right now we already know that this m and n satisfy either of the boundary condition 13a, 13b or 14. So we already know that this m and n both will satisfy the boundary condition, and we have already seen that if if they satisfy the boundary condition, then this quantity, which is Pwmn from a to b, is equal to 0. That is the content of the previous two theorems. So it means that if it is 0, then this part is simply 0. So it means that minus b a to b m square s plus n square s rs ds equal to 0. Now if you look at the integrand is what, this is all positive, and r is either positive or negative, but it cannot be 0. So it means that a to b m square s plus n square s into rs ds is non-zero, because we have assumed so that r is never 0, either it is all the time positive or negative. So, it means that this quantity has to be either positive or negative depending on the sign of RS. So, it means that minus b into something which is non 0 is equal to 0 implies that we have only option, that is b equal to 0. When b is equal to 0, it means that lambda is real. Why? Because lambda we have assumed that it is a plus ib. Now, if b is 0, then we have only option, that is lambda equal to a. So, what we have proved here, that your eigenvalue is purely real, and that complete the proof. So, it means that what we have proved here, that that if the hypothesis of theorem 15 holds, means we are considering the regular Sturm-Liouville boundary value problem with the boundary condition either separated boundary condition or periodic boundary condition, and if RT is either positive or negative, then all the eigenvalues of the Sturm-Liouville boundary value problem are all real. That is the content of this theorem, and let us move ahead and let us consider one very important application of the Sturm-Liouville problem, and that application is the expansion of a class of function in terms of eigenfunctions. So, that is the content of this theorem 21. So, let GT be a continuous function defined on closed interval AB and satisfying the boundary condition either 13a, 13b or 14, and let us assume that we have certain boundary eigenfunctions, let us say x1, x2, xn be the set of eigenfunction of the Sturm-Liouville problem 12 and 13a, 13b or 12 along with 14. Then you can expand your GT in terms of these eigenfunctions, that is C1 x1 t plus C2 x2 t and so on, Cn xn t and so on. So, here all these xi's are eigenfunction of the Sturm-Liouville problem, and here you can calculate the coefficient say Ci by the following formula, that is Cn from a to b Rs xn square s ds equal to a to b Rs gs xn s ds. Now, if you look at, we already know Rs, we know gs, we know xns. So, we can say that this quantity is also non-zero, because Rs we are assuming that it is positive and this xn square is again positive. So, it means that Cn you can easily find out by dividing this term. So, it means that you can get the values of Cn, and once you have all the Cn's, you can write GT in terms of these xi's. So, that is what is the content of this theorem, and this is proof is quite easy. Let me write it here. So, proof is this, that you have g of t equal to C1 x1 t plus C2 x2 t and so on. So, Cn xn t and so on. So, what we try to do here, we just multiply both sides by RT. So, RT GT equal to C1, let me write it here in a summation form, Ci RT Xi t, right. Then what we try to do here, we just multiply by say xn say. So, let us multiply both sides by xn and integrate with respect to t. So, we will get a to b RT GT xn t dt, and here what you will have, here you have, let me expand it, it is xn t into summation, it is a to b summation Ci RT Xi t dt, right. Or if you want to write it in a simpler form, this is what C1, your integration of a to b RT x1 t xn t dt plus C2 a to b RT x2 t xn t dt and so on. Here it is Cn a to b RT xn square t dt and so on. Now, we have already discussed that these eigenfunctions are orthogonal to each other with respect to weight function RT. So, it means that if n is not equal to 1, then x1 and xn are two distinct eigenfunction. So this has to be say 0. So by orthogonality property this has to be 0, similarly this has to be 0. The only term which is left non-zero is this term where we have m equal to n. So it means that here using this property that a to b rt xnt xmt dt is equal to 0 when m is not equal to n. So using this orthogonal property we can see that a to b rt gt xnt dt is equal to cn a to b rt xn square t dt, and we already know that this term is going to be non-zero. So by dividing this term we have cn is equal to a to b rt gt xnt dt divided by a to b rt xn square t dt. So once we have cn, and this you can write n for all n greater than or equal to 1. So it means that you can expand your gt in terms of x and t, and using the following formula to find out the coefficient here. So that is very important use of Sturm-Liouville boundary value problem, and we have seen some of the application in expanding say given function in terms of Legendre polynomial or Bessel's polynomial and so on. In Legendre polynomial we do not have any weight function and we do not require any say boundary conditions. So we simply say that we have already seen this kind of application in terms of Legendre polynomial and Bessel's functions. So now let us move ahead and discuss another important boundary value problem. So here this boundary value problem is that you consider a finite rod, right. So here finite rod is that it may be considered a metal rod. So one end is x equal to 0, another end is x equal to c, and we want to look at the temperature distribution on this finite length rod. So we assume that its faces are insulated, and further assume that the temperature distribution in the slab is denoted by f of x from 0 to c. So sorry, this is temperature distribution at the initial point is given by f of x between x to c, and let k is a constant denote thermal diffusivity for the given material. So this k is a constant depending on the material of the metal, basically metal of the that rod. So now if we use a model to write down the mathematical formula for this temperature distribution, that we have the following partial differential equation, that is w by w t x t equal to k w u by w x square x t comma t, and x is lying between 0 to c and t is greater than 0, and on the boundary since it is insulated, and so w by w x at x equal to 0 is 0 and w by w x at c comma t is equal to 0 for all t greater than 0, and the initial, so these are the boundary conditions and this is your initial conditions. Initial condition is that the initial temperature at time t equal to 0, your initial temperature is ux0 equal to f of x, that is what we have given here. So now we wanted to solve this using the Sturm-Liouville boundary value problem. So far we have not discussed this, how to obtain this this problem, and we have not discussed any property of this equation, this partial differential equation, which is commonly known as heat conduction problem or heat equation. So let us assume that we know how to define partial derivative. So let us if you are not gone through the partial differential equation, so let us assume that we have a partial differential equation, some equation related with partial derivative, and let us try to solve this. So to solve this, we simply say that observe that this is a linear boundary value problem given as a partial differential equation representing conduction of heat in a finite slip under preassigned boundary conditions. So, now let us assume that the solution of this problem, which is solution means uxt we are searching for, uxt represent the temperature distribution at the point x at the time t, right, and we want to show that let us assume that the solution of uxt has the following form, that is x of x into t of t. So, it means that here solution can be separated function of x and t. So, let us assume that uxt equal to x of x and t of t. We will discuss later on that why we assume this form of the solution. This is known as separation of variable form of the solution. So, here we assume that x here x is the function of small x and t is function of temperature here. So, let us calculate w by w x. So, when you calculate this, then it is total derivative of x and tt, and w2u by w x square is x double dash tt. Here this x dash is basically total derivative d by dx of x, and t dash is basically d by dt of tt. So, here this represent the total derivative, and partial derivative is given by these w by w x and w2u by w x, and similarly we can calculate w by w t, and it is xx t dash t. So, if you look at our equation is what? Equation is basically w by w t equal to k w2u by w x square. So, when you use this, this is what t dash t xx equal to k times this x double dash and tt. So, divide by your x into t. So, let us divide by xt, here also you write xt. So, when you divide by this, what you will left? This will cancel out, and here this x will cancel. So, we have t dash t divided by kt, you take k here. So, t dash t divided by kt t equal to x double dash upon x. Now, here if you look at, this is the function of t alone, and this is the function of x alone, and this can be equal only when the ratio is a constant value. So, let us say that the constant value is some minus lambda. We will see why it is minus lambda. You can use plus lambda, no problem, it is just a constant. So, using that, since this ratio, this is a function of t, this is a function of x, this can be equal only when each ratio has to be a constant. So, let us denote that constant as minus lambda. So, we have this equation, and we have also boundary condition. Boundary condition is what? That w w x is 0 t is equal to 0. So, if you simplify this is what? X dash 0 t t is equal to 0, and here we have x dash c t t equal to 0. Now, since we are assuming that we are looking for a non-trivial solution, so it means that none of this x of x and t t are trivial solution, means these are not 0 solution. So, it means that if t t is non-zero, so this equation this condition satisfy, means that we have x dash 0 equal to 0, and similarly since t t is not identically 0 solution, so we can say that x dash c is equal to 0. So, it means that not only we have two set of conditions, that is t dash t upon k t t equal to x double dash upon x equal to minus lambda, also we have boundary condition, that is x dash 0 equal to x dash c equal to 0, and here we have assumed that t of t is not equal to 0. So, it means that now our partial differential equation is now reduced to two set of boundary value problem in terms of ordinary differential equation. So, this is one set of boundary value problem, that is x double dash x plus lambda x of x equal to 0, and x dash 0 equal to x dash c equal to 0. So, this is a boundary value problem in terms of x of x, and we have another differential equation t dash t plus lambda k t t equal to 0 here. So, here we do not have any boundary condition in terms of Tt, but we have a one condition left, that is the condition, initial condition, that is u of x 0 equal to f of x, that we can utilize little bit later. So first we try to solve this equation number 30. This is a boundary value problem, and if you look at this is a Sturm-Liouville boundary value problem. So here we can apply our discussion of Sturm-Liouville boundary value problem to solve this boundary value problem. So let us solve this, and here since lambda is a parameter and lambda can take distinct values, so lambda equal to 0, lambda greater than 0 or lambda less than 0. So we look at these conditions separately. So first let us consider the condition that lambda equal to 0. So when lambda equal to 0, our equation reduced to that x double dash is equal to 0 and x dash 0 equal to 0 and x dash c are 0. These are the boundary conditions. So when you solve this x double dash x equal to 0, your condition is x of x is equal to you write it c1 c1x plus c2. You have to find out this c1 and c2 using this condition. So when you see that, you will say that x dash 0 is 0 means this is 0 equal to c1, and x means because x dash is basically c1 basically. So x dash 0 is 0 means c1 equal to 0, and x dash c equal to 0 means you have what 0 equal to c1. So that is what we get. So it means that we have only c1 equal to 0. So it means that x of x has to be c2. So it means that solving this we get x of x is equal to just a constant value. So let us simplify, for simplification let us assume this as 1 by 2. We will see why this we are assuming 1 by 2. In fact you can use any constant alpha, beta, gamma, anything you want to use it, but for the simplification we are assuming it is 1 by 2. Now let us use, so it means that this lambda equal to 0 is an eigenfunction, is an eigenvalue, and the corresponding eigenfunction is a constant value. Let us say that it is 1 by 2. So lambda equal to 0 is an eigenvalue. So now let us consider lambda greater than 0. So assume that lambda equal to alpha square, because lambda is positive, so let us assume that alpha is square and alpha is belonging to real number. So when you put this value lambda of alpha square, then we have equation as x double dash plus alpha square x, and boundary condition these x dash 0 equal to x dash c equal to 0. So when you solve this equation x double dash plus alpha square x, we have relation c1 cos alpha x plus c2 sin alpha x, and now let us find out this c1 and c2 using the boundary condition. So let us find out the derivative of this. X dash x equal to minus c1 alpha sin alpha x plus alpha c2 cos of alpha x, and we have x dash 0 equal to 0. So this implies that your alpha c2 equal to 0. Now alpha cannot be 0, so c2 has to be 0 because alpha is positive real number, alpha is any real number, and if we take alpha equal to 0, then lambda has to be 0, and which this case we have already considered. So here we assume that alpha is some value which is not 0 basically. So here c2 has to be 0 and x dash c equal to minus c1 alpha sin alpha c equal to 0. Now since c2 is already 0, so if we take c1 equal to 0, then we have only trivial solution which we really don't want. So what we try to do here, we try to show that this alpha sin alpha c has to be 0. So we want c1 non-zero, since we are searching for non-trivial solution of the problem. So therefore only choice left is that alpha has to be n pi by c. So here we assume that sin of alpha c equal to sin of n pi. So it means that alpha c equal to n pi, where n is running from 0, 1, 2. In fact n is coming from integer values. So here let us assume that c1 can be any constant. So let us assume that it is 1 for the time being, and eigenfunctions we have x of x is equal to cos of n pi x by c, where n is from 0, 1, 2, and your lambda is basically n is alpha square, that is n is square pi square by c square. So it means that here we have another set of and n is from 0, 1, 2, any number here, any natural number, in fact any integer number. So here eigen values are n square pi square by c square, and the corresponding eigen function of x of x equal to cos of n pi x by c. So now let us consider one more term, that is one more possibility, that is lambda less than 0, and here assume that lambda equal to minus of alpha square, alpha is positive, then the boundary value takes the following form: x double dash minus alpha square x equal to 0 and x dash 0 equal to x dash c equal to 0. So when we simplify, we have this relation x of x equal to c1 e to power alpha x plus c2 e to power minus alpha x. I leave it to you that when you put this condition x dash 0 equal to x dash c equal to 0, then we have only this thing, that x of x has to be 0. So when you use these condition, then we have only a trivial solution. So we do not want a trivial solution. So it means that this lambda less than 0 is not eigenvalues. So it means that we get only two set of eigenvalues. One is corresponding to 0. So lambda not equal to 0 is an eigenvalue, and corresponding eigenfunction is basically some constant. Let us assume that it is 1 by 2, and another set of eigenvalues we have obtained for the case when lambda is positive, that in that case we assume that lambda equal to lambda n, where lambda n is equal to alpha square, which is given as n pi by c. So here we write lambda n as n pi by c whole square, where n is 1, 2, 3, and because if we put n equal to 0, then it is reduced to this lambda naught. So here we assume that n is non-zero integer value. So it means that these are the eigenvalue, and the respective solutions of boundary value 30 is corresponding to lambda naught. We have this solution, so it is eigenfunction corresponding to lambda naught equal to 0, and corresponding to lambda n we have eigenfunctions given by this. So when we basically eigenfunction means non-trivial solution of the boundary value problem. So when you summarize this, we can get all the possibilities of x of x. Now solve the other part, that is in terms of t of t. So that is the problem we have here, that is t dash t plus lambda k t t equal to 0. Here you already know lambda, and you have k is already given because material is given. So you can simply solve, and this is simple ordinary differential, first order ordinary differential equation, and the solution of this problem is given as t t equal to c3 exponential of minus lambda k t, and c3 is an arbitrary constant. So let us assume that c3 is equal to 1. If you do not assume, then also you can write it, but for simplicity I am writing c3 is equal to 1. Then substituting the eigenvalues. So eigenvalues is that lambda naught equal to 0. So when we put lambda naught equal to 0, then your tt, which we denote as t naught t, it is coming out to be 1. And when you take lambda as lambda n's, then your t and t, which is the solution corresponding to lambda n, it is exponential of minus n square pi square k t upon c. So here we have solution obtained for lambda naught equal to 0, and solution is given by x naught x into t naught t, and since x naught x is 1 by 2 and t naught t is coming out to be 1 here. So this is for lambda naught equal to 0. So uxt is equal to u naught xt for lambda naught equal to 0. Similarly, uxt is un xt when we are assuming lambda as lambda n and n equal to 1, 2 and so on. So in this case your solution is x n x into t n t. So x n x is cos n pi x by c, and t n t is exponential of e to power minus n square pi square k t upon c square. So we obtained the solution in different cases, that is lambda naught which is 0 and lambda n when n is from 1 to 2. And we here we utilize one more thing, that if we have some solutions, say y1 and y2 are solution of linear problem, then their linear combination is also a solution of the that linear homogeneous problem. So here we are utilizing the property of homogeneity, that your boundary value that your problem is homogeneous and problem is linear. So here we can apply that if we have solutions, then linear combination of solution will also be a solution. So here linear combination of, so here we say that a naught and u naught. So a naught u naught is a naught by 2 plus a n, and this is your x n u n x t. So we already have solution u naught and u n. So we say that a naught u naught plus a1 u1 plus so on an un will also be a solution. So, if these are solutions, then linear combination of these will also be a solution. So, utilizing this, we have solution u x t equal to a naught by 2 plus summation n from 1 to infinity a n exponential of minus n square pi square k t upon c square into cos n pi x by c. So, here we have this solution. Now, the only thing is that this is a complete solution provided we know these coefficient a naught and a n's, and because so far we have utilized only the boundary condition, we have not utilized the initial condition. So, we have the possibilities of AIs. So, to obtain these AIs we can use the initial condition, that is u of x 0 equal to f of x. So, using this we can simplify this. So, we can write it f of x equal to a naught by 2 plus summation n is from 1 to infinity your a n and cos of n pi x by c, right, and then we can obtain our coefficient a naught and a n. So, here what we do, here we just multiply by cos n pi. So, here what we do, here we utilize the orthogonality of cos of n pi x by c. So, you multiply by cos of m pi x by c on both the sides and integrate. So, it means that you just multiply here f of x and between interval, I think it is 0 to c, we have written 0 to c f x into cos n pi x by c dx equal to this a naught by 2 integral 0 to c cos of n pi x by c m pi x by c dx plus here it is what, here we have this a n cos of n pi x by c into cos of m pi x by c d of x and 0 to c. So, here using orthogonality you can find out the value of a naught by 2. So, you consider the case when m is not equal to n, then you can find out the corresponding values of coefficient. So, this part I am leaving it to you, and you can easily find out the coefficient a naught and a n using the orthogonality of cos n pi x by c, as we have done the expansion of g x in terms of eigenfunctions. So, here I will end our lecture, and in this lecture what we have seen the that how this Sturm-Liouville boundary value problem is useful in solving many important problem. So, first is that it is used in expansion of a given class of function in terms of eigenfunctions. Another is solving real world problem such as partial differential equation in terms of separation variable form. So, we have seen one example based on this. So, here we end, and we will continue our discussion in next lecture. Thank you very much for listening. Thank you.